Hey everyone, welcome back. Looks like we just have one more section to get through in Chapter 9 since, as mentioned, I've gone somewhat out of order. But it's a good time to review something mentioned in Section 13, which 13 normally comes after 12, of course, but we've already covered it in our videos, and that's because Chapter 9, Section 13 is essentially a review of Chapter 7, Section 12, where we covered the oxidation of primary and secondary alcohols to carbonyl compounds, either aldehydes or ketones. And we covered the difference between these two oxidizing agents. PCC, pyridinium chlorochromate, is a milder oxidizing agent, and PCC will convert a primary alcohol to an aldehyde and then stop. It doesn't oxidize it any further than that. Jones reagent is harsher and will oxidize a primary alcohol all the way up to a carboxylic acid. In fact, Jones reagent will also oxidize an aldehyde up to the corresponding carboxylic acid. And either of those two reagents will give the same result when oxidizing a secondary alcohol. The only possible oxidation product is a ketone, so it doesn't matter which of those reagents you use. They are interchangeable when it comes to oxidizing secondary alcohols. So what if you wanted to do the opposite? What if you wanted to reduce a carbonyl compound to the corresponding alcohol? This needs a hydrogen. That's much more better. There we go. That can be done with a hydride reagent. And we're going to learn about two of them, sodium borohydride and lithium aluminum hydride. And the structures of these two compounds are, as you see here. Of the two species, sodium borohydride is less reactive, and lithium aluminum hydride is more reactive. And that is to do with the nature of the boron hydrogen bond versus the aluminum hydrogen bond. The aluminum hydrogen bond is more polar than the boron hydrogen bond. And so that makes the bond more reactive. Now, both of these have the ability to give up hydride ion, H-, which is a very different critter from H+. So both of these anions can, if you will, spit out H-. That's a hydrogen with a lone pair of electrons and a minus charge. So recall, hydrogen is actually three possible oxidation numbers. Of course, 0 in the pure element, H2. Almost always when hydrogen is combined with something else, it has an oxidation number of +1. And in those other cases, ordinarily in combination with metals and certain metalloids like boron, then hydrogen has an oxidation number of -1. And that's the case here. So this hydride ion is a very strong reducing agent. It's also a very strong base, and we might sometimes see it used for that. But these two reagents have different reactivity. That's going to become, I predict, though it's possible my prediction will be wrong, but I predict that will become more relevant for us in Chapter 10 when we go on to reactions of carboxylic acids and esters. Both of them react exactly the same towards an aldehyde or ketone. And with an aldehyde or ketone, they are again interchangeable. Both of them will reduce the carbonyl to an alcohol group. So it will reduce a ketone to a secondary alcohol and an aldehyde to a primary alcohol. And again, for those purposes, these two reagents are interchangeable. It doesn't matter which you use. In real life, they are very different in their, maybe I shouldn't say behavior, but let's say they're very different in terms of how we treat them, the amount of care that we have to show them. And we'll go over that. So I just wanted to give you some examples here. If we took cyclohexanone and treated it with sodium borohydride, this is nearly always done in either aqueous solution or some kind of alcoholic aqueous mixture. That's normally how we do a sodium borohydride reduction. And then afterwards, we're going to do what's called a workup step. We're going to add dilute acid to the mixture. And that's going to have a number of effects, which we'll get to in a moment. Notice the numbering of the steps. That's extremely important. it's very important to notice when you see numbered steps like this versus when there are no numbers. When there is no numbering to the steps, what that means is that everything there above and below the arrow and all reagents you just toss in all at once. When you see numbered steps like this, what that means is the following. We're going to take our cyclohexanone in this case, though I could have chosen any other aldehyde or ketone. We're going to dissolve it up in aqueous methanol, and we'll throw in the sodium borohydride, and then we will wait until everything's done reacting. And there's ways that we can test for that and make sure that our starting material is consumed, for example. Only after everything's all done reacting, then we will very carefully add dilute aqueous acid. And that will do a number of things. That will, first of all, neutralize any ionic species. As it turns out, we don't immediately get this alcohol. We actually get the conjugate base, O-. And so the acid will put the proton back on that. The acid will also destroy any leftover sodium borohydride, and we will get hydrogen gas and probably something like sodium borate or something like that. Something inorganic anyway. The major organic product will be the corresponding secondary alcohol, cyclohexanol, that you see over here. If we were to do the reaction with lithium aluminum hydride, which we lovingly call LAH, and you may do so as well, now you'll notice we're not using protic solvents. Protic solvents will react exceedingly violently with lithium aluminum hydride. Water in particular will get you a big fire for sure. Methanol or an alcohol may be a slightly smaller fire, but still dangerous. So we need to use an aprotic solvent, and diethyl ether is generally what's used, though you can also use tetrahydrofuran, the structure of which we talked about in Chapter 8. If I were doing it in real life, I would use diethyl ether if at all possible. So the ET here, that stands for ethyl group, C2H5. This compound is essentially CH3CH2O, CH2CH3. So diethyl ether. And if I were doing it in real life, that's what I would do. I would dissolve my ketone or aldehyde in diethyl ether. I would cool it down a ton, and I would very carefully, don't try this at home, kids. I've had a lot of experience with these reagents, and LAH is much more dangerous and much more reactive than sodium borohydride. But what I would do is I would very carefully and gingerly pitch in small amounts of the lithium aluminum hydride. It's a solid. It's a powdery, whitish or grayish solid. All again while cooling the flask. I would then wait a while and test to see that my starting organic material is gone. And then I would do my workup. And you can do it by adding dilute aqueous acid. In fact, even just water is enough. So if you put H3O, dilute H3O plus, or even just H2O, it's fine as far as I'm concerned. And you'll get some ideas of what the varying different ways of writing this down are when you compare to your book and you compare to the OWL problems and so on. That will give you some idea of what the allowed variations are, if you will. But here you can put either H3O plus or H2O. With sodium borohydride, it's less reactive. I would rather use dilute acid with that one. And one question that comes up here, since I'm dwelling on the different reactivities here, which I think is good. I think it brings it alive for you guys and helps you understand that these are not just letters and numbers. These are actual things. You can go put your hand on a bottle of these things. Anyway, you might be wondering, well, if LAH reacts with water, doesn't sodium borohydride react with water and with methanol? Answer is yes, absolutely it does. But it reacts much more slowly than lithium aluminum hydride, and in fact would react faster with the carbonyl compound. So you're generally pretty safe using a protic solvent with sodium borohydride, and that is usually what we do when we use sodium borohydride, not LAH. That will react very violently with a protic solvent. So generally an ether solvent is used, and if I could use any ether solvent I wanted, I would use diethyl ether. It's easy to get, it's cheap, you can get it nice and dry and freshly distilled and so forth. And best of all, its boiling point is something stupid like 35 degrees Celsius or something. So it's very, very easy to get rid of at the end of the reaction. So that would be my solvent of choice. That's what I would try first. And like I said, when the reaction's complete, you could add dilute aqueous acid. That's fine. And if you write that, it's completely fine. It's not wrong. But I was, so to speak, taking you into the lab with me and doing this reaction. So we pitched in our LAH in small portions. We've stoppered our flask up. We've gone for a walk or whatever it is we do. We come back. We run thin layer chromatography to see if our cyclohexanone is gone, and it is. So we can work up the reaction. And the way I most like to work up this reaction is, again, keeping it nice and cold. I will pitch into the flask little pieces of ice. So just water, but ice, so it's also cold. And it's pretty amazing how violently even that reacts with LAH. You'll see hydrogen gas bubbling out. So again, don't light a match. And once the bubbling is quieted down, then you can proceed with your extraction and your drying it over a drying agent, you're filtering off the drying agent and evaporating off the solvent. All that is safe to do once the initial reaction is done. But again, these two reactions will effect the same thing. Both of them will give you the corresponding secondary alcohol. And likewise, if we started with an aldehyde, such as benzaldehyde, I'm here just using benzaldehyde as an example, LAH and diethyl ether, followed by an aqueous or acetic acid, a dilute acid workup, will give you the corresponding primary alcohol, in this case, benzyl alcohol. And again, if we had instead written here step 1, sodium borohydride, water and methanol, followed by dilute acid workup, same result, same exact result. So for aldehydes and ketones, these two reagents are interchangeable. That's not going to be the case for carboxylic acids and esters, which I believe that we will get to in chapter 10. So other than that, I think that's pretty much it for chapter 9. So this will be our last video for chapter 9. After this, though, we're not going to go straight to chapter 10. We're going to take a detour through carbohydrates. So that's what we'll cover next. So until then, have a good day.